I'd actually like to expand on this discussion with the WRMSPE. So when we calculate error measures per series, across series, then actually there are usually 3 dimensions along which we can potentially average, which would be the horizon, the rolling origin, or the different time series. So just to quickly explain that, so let's say this is our input window, and now let's say we have an output window for which we forecast. So that would be different horizons, right? So we have here 1 step ahead forecast, a 2 step ahead forecast, 3 step ahead forecast, and so on. Rolling origins would now be that we just shift our origin 1 value into the future and then the next value. So basically here the origin that shifts forward. And now we could obviously do all of that for different time series. We could have time series 1, time series 2, for which we do exactly the same with the windows and the rolling origins. Exactly. And now, well, so we could average in this dimension across the horizon along this dimension for the different origins, or across this dimension, which are the different time series. And now it is important that each of these dimensions can actually collapse. So you can easily think of a situation where we forecast only 1 horizon, only 1 origin, or only 1 time series. And this can then cause problems with divisions by 0 if some actuals happen to be zeros or small numbers. Yeah, if the actuals or forecasts are close to 0, and then that can make the measure blow up or degrade in other ways. Yeah, and so in general, what we want to do always when we calculate errors, on the one hand, we want to aggregate, and on the other hand, we want to divide by a normalizing factor. And now the problem that usually happens is that if we divide first, we have problems with division by 0 and numerical instability, right? If it's just like because we are dividing just by single values. But if we aggregate first, now we need to make sure that what we aggregate over is actually, apples and apples, so on the same scale. And that usually means that we don't want to aggregate over series from different series before we normalize. But already within single series there can be problems. We get to that very soon when we talk about the WAPE. The weighted mean absolute percentage error, that was actually so Belt in 2017 and then Kolassa and Schütz in 2007, they argue for this measure to be used in demand forecasting. It's called weighted because the MAE, so you might ask, well, why is this weighted? Where are the weights? I can't see any weights in the formula. So that's because the MAE can actually be seen as a weighted, scaled version of the MAPE, and that's what the weighting is. So you can say, well, the MAPE, the MAPE is scale free. Every series is the same, and then the MAE you scale, you weight with the value of the series, right? With the kind of scale of the series. The WAPE is also sometimes called MAD by mean ratio, which makes sense if the actuals are all non-negative, because then these absolute values here, for example, down here, right? So this is now basically just the mean. If you put like 1 divided by n up here and down here, right? Then on top you have the mean absolute error, that is also sometimes called mean absolute deviation, MAD, and then down there you have the mean. So that's where this name comes from. Yeah, and I mean, as I just discussed, it has these advantages that if your test set is big enough, you're dividing by a sum over something, so less likely to divide by 0. But obviously if your test set is only 1 value, then don't have any advantages over the MAPE. Okay, so now this was an absolute measure. You can think of measures along this line that measure bias or that are quadratic, right? So if you just remove the absolute values, you get this weighted bias percentage error. And then you can also use squared errors instead of absolute errors. That gives you this measure here. Well, you could obviously think about why do you have here absolute value, why don't you square and also have a square root and so on. So there are different ways you can potentially introduce this WRMSPE, but I've kind of convinced myself that this version with the absolute value in the denominator is kind of the best way to go. Yeah, and so as discussed before, if you have a quadratic measure that this measures and that measures the standard deviation for an unbiased model. Okay, and then, well, because in retail e-commerce it is beneficial to monitor both bias and overall error, then some practitioners have come up with, okay, well, what about we just combine the WAPE with the bias measure and we just maybe sum them up and have in this way one number that tells us how good we are. So that has been proposed. I mean, yeah. Okay. Now just to get back to this idea, so the WAPE, yeah, it divides by this sum. And now one question is, well, what should this sum run over, right? So it can run over each series individually. It could also just really run over all the series, right? You could at first sum everything and then afterwards divide. So if you run over all series, so, you know, you have in the denominator here this sum, here this sum, you do that over all everything, all series, all the horizons, all the origins, and also in the denominator you sum over everything, and then at the very end you divide. You can do that, but it is what you do now is essentially an MAE. So a scaled measure that you then afterwards scale globally to be a percentage. So yeah, it's essentially the same as MAE, but maybe slightly more interpretable. But obviously, well, as in the MAE, series with higher values get more importance in the error, right? Because you summed first the errors and then afterwards you divide it. On the other hand, if you run the sum per series, you get a scale-free measure. Yeah, it only works if we have more than one forecast in the test set. Otherwise, it degrades to the MAPE. And if the whole test set is 0, then again, we have the problem of dividing by 0, right? So it is a bit of trade-off between, do I have only one value? Could that be 0? Do I have only 5 values? Could all of these be 0? Or do I have like a large enough test set? So, okay, so what are the advantages of the WAPE? It only divides by 0. If the whole test set is 0, it is minimized by the median of the forecast distribution, which is the WAPE, and then the WRMSPE minimized by the mean of the forecast distribution. It is interpretable as a percentage. I think that's very important, and that's why people usually like to use it, but it has some quite important disadvantages. So Rob Hindman recently had a blog post where he shows that it is only a consistent estimator when the series is stationary. And it can be seen as a rel MAE where the benchmark method is a constant 0. So, and then what that means is it works well if a constant 0 is a reasonable benchmark, right? So basically here, okay, we can't really see that anymore. So here in the denominator, right, you can think of, well, here if I here like in the denominator, I could subtract the benchmark, right? YT minus YT hat of the benchmark. And now if this benchmark is a constant 0, this kind of goes away and we are left with just what is here and here, down here. Okay, exactly, so you can see it. Okay, and now this point, right? What does this mean? That it is only a consistent estimator when series is stationary. So let's think about, you have a series that has a trend. Yeah, this is my test set, okay. And now I have a forecast, and that forecast, you know, is kind of just a little bit off, okay. And actually, well, I have like a rolling origin and I have two test sets, right? So like test set 1, test set 2. And in both of them, I am just a little bit off with my forecast. So now the thing is that this error, right, this difference between the actuals and the forecast, that is the same in both test sets, right? If this is test set 1, test 1, and this is test set 2, test 2, right? This one and this one. Yeah, so the errors are the same, but the actuals in test set 2 are a lot higher than in test set 1. So what does that mean now for our measure? It means that what we have up here is the same, and what we have down here is growing. So the overall WAPE is getting smaller. So basically, the WAPE for test 2 is smaller than the WAPE for test 1. And then you can sell that to your manager and say, oh, we are actually getting better, our forecasts are improving, when in reality they are just the same, right? So the error has not changed. So that's a problem, a big problem that these measures like WAPE, WRMSPE, and so on have, right? Okay, so the question is, well, how can we fix that? Well, if a constant 0 as a benchmark is not good, then maybe we should use something else like naive, right? So which we are back to this REL MAE.